Alright, so welcome everyone. I'm Valdis Solsprans. So this course will be in English. Since I understand you are mixed, there's lots of different courses together. So as I understand, most of you are from Humanities, is that correct? Right? And most of you are master's students, right? If I understand correctly, right? At first year or second year? First year.
Second semester.
Okay. Alright. So the question, of course, is how much programming experience do you guys have? None?
Previous semester you were the teacher for us for the web development.
Oh, okay, excellent. All right, so you know a little bit already. It'll be easier. Okay, excellent. All right. Okay, that's good, actually. Right, so Python you'll find much easier, I think, than JavaScript, I think. Right, if you are able to finish the JavaScript homework, I think you'll have no problems with Python in general. So I will do a little, today we'll have sort of just get acquainted, and maybe I'll talk about of course, the main thing is the grade requirements. I'm sure you want to know that, right? So the grading schema, this course has been running for about 5 years. I've been programming in Python for like 20 years, but this course has been 5 years old. Yeah, so the grades are 30% attendance, so these daily, weekly quizzes, which you already know from the other course, right? Short 5 question answers, those will give you 30% of the grade. There will be a 30% midterm project, solo. Again, open book, you do your work, nice comments, right? And final group project, you can do it solo or you can do it in a group of up to 3 persons, 3 people, 3 students. And also there's an option to write an essay or a paper or a presentation. Want to raise your grade, gain extra points, so you can get 11 in your, well, or 11, or I don't know what you want. So that's a possibility. Now, again, so the aim of this, or the goal of this course is for you to get comfortable with Python programming language, which is not just for programmers, it's actually for everyone, right? Useful for any type of research, many different applications. Now, what else is needed? I know some of you here are from a second course. Actually, I have 2 courses, right? I don't know who is from the other course. There's DIP720 and there's another DIP720, right? So one Ortus page has all the materials, right? But there's like 3 or 4 students who have another course. I'll show you here. Okay, so it looks like everybody's here. Right, this is the main course, right? 679-864. But I had a few students. I'll show you which ones they are. You'll find yourself. Maybe they're not here. 1, 2. How many of you are here? 4, 6, 11. So it looks like this may be just the main one. I don't know where they are because I suddenly just appeared like this morning, which is basically, well, there's the other one. This one here. Yeah, so you'll see this page. If your course page is like this leads to the main page, right? So you are a guest students, but I guess you are all here for the main page, right? Yeah. So I don't know what happened to these 4 people.
There are two guys.
Yes. You guys came in, right?
Yeah.
So you are from that group.
Perhaps, yeah.
Perhaps, right?
I found the main page anyways.
Okay, you should have access because I added you separately. I added the 4 persons, right? Added them to this main page, so you should have access. Everybody should have access to this main page. This one here, right? 679-864. All right. So weekly quizzes. And what else is needed? Well, of course, computers, right? Will install Python during the course. It's not absolutely required that your Python works on your computer. It's possible to finish the course using just cloud resources, remote resources, right? If something your computer is, I don't know, it doesn't work very well, or you're using university computers, it's possible. So it's not a requirement. What else? Oh yes, and I will have all the lectures will be available as videos. So there's a playlist. Right now, if you click on this videos playlist fall 2024, it should be empty. And yeah, it's empty. So I'll add the videos from today. I will add them later on. Okay, so let's get started. And today we will just get a little introduction to Python, right? Maybe we'll start with a little history lesson. I think we can do that. A little short history lesson. Let me see if I have it here. What's happening here today? I'm late. Oh yeah. So brief history of computing and data. And again, there's some overlap with, I think, I don't know, I might have shown some of the slides in the previous course, right? So a brief history of computing and data, right? And how we get to the Python part, right? Sort of like this famous, what the heck is that actually, right? I have asked, I don't know if you've seen this picture, right? Right, you see some markings there. Can you see this? It's kind of hard to see on the slides, right? But it's very old. So how old is it, do you think?
Stone Age.
Yeah, it's Stone Age. Yeah, well, it's certainly Stone Age. It's about 18,000 BC, so 20,000 years old, right? Uganda, Ishango bone, and there's some markings there on that bone. And well, researchers, they think these were used for counting, maybe some calculations, some primitive calculations. What were they counting? Lions, or I don't know, pigs, or I don't know, something, or maybe, you know, stars. We don't know exactly, but yes, it looks like there's some primitive arithmetic. Of course, then we get to Babylon. We have abacus, skaitikļi in Latvian. Who has used abacus? Who knows what to use? Anyone? No one? Maybe your grandma knows how to use them. Like maybe 20 years ago, abacus was used quite a bit actually. Sometimes if you go to countryside, there were old cashiers who were really good at this. It was faster than using a calculator actually, right? So still, you can still see them around sometimes, right? So yeah, it's a very, very old computing device for calculations, right? Adding. Around the time we also have Library of Alexandria for storage of data. Again, contrary to popular knowledge, it was not burned down in one day. It was actually a gradual process how the information was just sort of like displaced and lost, right? Didn't happen over one weekend. But yeah, suddenly it was gone. One of the first big major libraries, storage of human knowledge, right? So we have this simultaneously. We have some computing going on, and we also have this library storage, right? And I don't know if you've seen this picture again. So this is a recreation. This is a remake made from from the old device. But it's about 2,000 years old, and I usually ask, where is it from?
Time travel.
Give me?
From time travel.
Oh, I like that one. I like that answer. Yes, but yeah, you can see that. But maybe a little hint is the background. Can you see the background? Yeah, where is that?
Binary?
Yeah, you see some. It's kind of green. Like I've seen. Where is it from? What do you think?
Greece.
Yes, of course, Greece. I mean, pretty much everything from Greece, right? Yeah. I've heard Italy, but no, it's Greece. It was discovered about on the coast of Greece. I don't know, like late 20th century. They rebuilt this, and it's basically first mechanical computer calculator. It was used for, well, obviously used for astrology. Always a big winner, right? Astronomy. And those days, astronomy, astrology, pretty much same thing, right? In those days, Olympics. I mean, however, of course, as a calendar. So they had, I think, 57 wheels. Had multiple wheels. You turn them, and it basically did calculations.
That was so small.
Yeah, I think it's part of the. It's a. I don't know. If it has all wheels. There's 1, 2. I see lots of smaller wheels. It's about, I don't know, like this. Yeah.
From what material it was made?
I believe copper. I don't know. I don't think gold. I don't think it was gold. I think it's copper. I'm pretty sure. Yeah, it's pretty famous. We could look up in Wikipedia where it is actually stored right now. The original, right? It's all rusty, but yeah. And then we have the Dark Ages, and we get next innovation, which is basically almost the same thing as the Greeks did. Was Blaise Pascal, the French philosopher, polymath who did pretty much everything in those days. Right, he even got a royal patent from Louis XIV for this machine. Right, it could multiply. You could even divide using addition and subtraction. So it is basically a calculator, but of course mechanical. You turn the wheels and things happen. All right. So, but I'm going to jump ahead already to the 19th century, already to Charles Babbage. Right, difference engine. And again, is this the real thing? What do you think? Is this one here? The one in the background, the picture. Is that the one he built? Do you think? No, it looks too good, right? It's too new, right? Yeah, so it's not it's a recreation. Well, it's a remake. Actually, even worse than that, he didn't really build a full difference engine, right? He could never get enough funding, 19th century, right? The story goes he basically had these great plans, but the money it was this whole monster, this mechanical monster. He just could not get enough money, but it's been proven it would have been a real first programmable computer, right? It would have actually you do arithmetic, derivation, power series, curve fitting, do a lot of things actually, right? And so it leads, of course, to Ada Lovelace, who was the first programmer by standards. Actually, it does meet the standards of programming, but the thing is, she was programming for a machine which did not exist. So she was also doing marketing. She was going around Europe and saying how great this thing will be, right? The program she has, actually, we see the instructions for the program was pretty interesting. For I think Bernoulli numbers, kind of cool thing actually, right? The program she wrote, but it was not actually working because there's no machine to run it from, right? So it's like one of the first what we call vaporware, right? You say you predict, you promise there's this great machine, this great new I don't know gizmo. This it's going to happen. It's going to be great, right? But you know. It will solve the world's hunger, but it doesn't appear, right? So, but yeah, she died too young, but didn't get to see actually the machine, right? So same goes for Charles Babbage. But basic idea, of course, was taken from what? From looms, from making patterns using looms, right? This is the early 19th century. You have these punch cards. You could draw a pattern, right, to make clothes. Right, it's a certain pattern, and that kind of inspired these machines actually, how to store data. Let's see, we'll see this. Yeah, and we get to actually again. I'm skipping, of course, centuries, but we get to Turing, right? Alan Turing, early 20th century, right? And he came up with this idea that you could come up with this Turing machine that you have some instructions and you have this infinite tape. We have this infinite tape for these instructions, and basically proved certain things, what kind of computations this machine can solve. It turns out pretty much all the modern languages, programming languages, they are so-called Turing complete. They can do the same thing than Turing machine, and vice versa. Turing's machine could have implemented these modern languages. They are equivalent in power, what they can solve, right? But you would not want to program on Turing's machine. It would be quite painful. I don't know. Getting hello world would take forever, right? There are some languages which try to approximate what Turing's machine is. I won't name the names because they're kind of obscene names, right? But they are very minimalistic, and yeah, they're basically for fun. They're not real. They're not a real production language. Not for real use, just for fun. But yeah, so Turing's machine was very influential. But again, when he wrote this late 1930s. There was no real computers. I mean, Babbage machine was gone. We didn't have we didn't have the computers, right? Yeah. Similarly, Alonzo Church. Again, this guy. There's no movie about him, but he proved actually there's something called Church-Turing thesis that his approach using something called lambda calculus, it led to functional programming. Is equivalent to this Turing machine, basically. His approach, same as Turing's approach, right? So Church-Turing thesis, right? Very influential as well. Now, but then we go, of course, to World War II, and there's actually, you could say sadly, but well, or luckily, there's huge progress as far as computing goes. Because what do you need to do? Well, there's two things, right? I'm talking about the Allied side. There's huge demand for two things. What do you want to use computers for? What kind of computations do you need to do in World War II?
Like encoding secret.
Yes. So one big use, of course, was trying to decode the German Enigma machine, right? This was one big. It drew a lot of adoption. You need to decode try to decode, and of course, eventually decode these secret messages. That's one. And second is kind of more classical one.
Calculations?
Yes. For what? Yes, for shooting things down. Yes, artillery. Yes. So, again, ENIAC, I believe, was the first Turing complete machine, actually. And I want to say this, it's interesting that basically this machine theoretically could emulate all modern machines, right? I mean, we could write a Python interpreter for it. right? And vice versa, we could write to emulate this machine. And this is due to this it being Turing complete, and also to the architecture. Somebody called John von Neumann, one of the great minds of 20th century. He came up with this architecture where data and instructions on what to do with this data, they sit on the same memory, basically, right? And it leads to very flexible situation. And this is architecture, pretty much I'd say 95% of computers use this architecture. So you might be asking, what's the other architecture? There's something called Harvard architecture, another Harvard, which separates the instructions and data. It's used mostly in smaller, some small special devices, but not in general computers, right? It turns out using this von Neumann architecture is very handy. Basically, we have a big slab of memory, RAM, or it could be also storage, SSD, right? But it basically has instructions and data, everything together, basically, right? And it's very convenient, right? So very flexible. Yeah. So now we go to data, again, a little bit more. So how do you store this data? We have computers, we have speed, but basically computers getting faster, maybe a billion times faster, maybe a couple billion times faster than the one in 1940s or modern ones, right? We have gigahertz. Then they didn't even have kilohertz, I think, the first ones, right? They were using, what were they using? Early, the first, what was this one using? What was they using for switching, for storing data? What do you think? What kind of technology? You could use switches, right? But so they need some sort of switching, you know, on, off, yes, no, 1, 0, 1, true, false. So what were they using for storing that? Any ideas? I used to have it on with me. Sometimes it was on a loan from the museum for storing 1 bit. It was like this big, 1 bit, not byte, just 1 bit. Tapes later. You could store tapes a little bit later, but actually for live RAM, they used vacuum tubes because that's all they had, right? So a question might be: so these days vacuum tubes are. Where do you see vacuum tubes these days? Anyone know where they still around? Anyone? No. Anyone listen to music? Have any music like high-end music fans, like meaning audio equipment? Yeah, they use them for high-end audio equipment. Some certain things, right? Because they have special characteristics. But there's another problem with these tubes. They used, I think they used about 8,000 tubes, so about 8,000 bits, 8 kilobits, or I guess 1 kilobyte. But there's a problem. You have 8,000 vacuum tubes. It's basically, like a lamp. Like the old style lamp, not LEDs, regular incandescent lamps, we don't use them in European Union anymore. Can you still buy them? I still have some at home, but I don't know if you can buy them in the store. If you go to the store, it's kind of hard. Somewhere, yes. But what's the problem with those lamps? What do you think?
They're like short life.
Yes, well, that's the main thing. First of all, they take, of course, lots of electricity. It took like huge power. Okay, but okay, let's assume you have power. But the biggest problem, yeah, they heat up. Due to the heat, they have short life. And due to statistically, you have, let's say, one, it has like life maybe, 30 days, or maybe, half a year of usage, right? But problem if you have 8,000, statistically, they will be failing pretty much every hour. At least one will fail. And you use the 1 bit of information somewhere, and it might crash the program, right? So basically, you had to have these technicians going around replacing lamps. It's really hard to write some programs, right? You program the lamps, and again, you have to re-enter the program, because of course also storage was really painful too. Entering the programs, you had to enter switches, right? So they didn't have programming languages in those days, right? You had to use a manual machine codes. Of course, very quickly we realized we need programming languages. So yeah, but we go down to our data storage needs, right? We have flat files. They came from punch cards, basically just like text files. Let's think of them text files, just a certain width, very basic. But then of course quickly there was need for databases. All right, and this shows quickly the growth of different ways of storing. SQL, 1970s. Have you had SQL lessons yet or no? Not yet. Maybe. Database. Yeah. Again, this is one of those things which was in 1970s technology, but it's still around, and it's going to be around forever, actually, I think, and it's useful to learn. If you are going to do any sort of research, any sort of analysis, right, of getting data, it's good to know some SQL. It's not. It was actually meant to be learned by pretty much most people. It's not that hard actually. So we have some other technologies, but now maybe let's do again another historical question. What is this? What's happening here? So this is cutting edge technology in late 1930s, so before computers. I believe it's a statistics bureau. Which country do you think it was?
Germany.
Yeah, it's a good guess actually. I would have guessed probably Germany too, but actually it's Prague, Czechoslovakia, right? Again, a little Kafka, a little bit of Kafka here, right? But so basically, the human is the computer. Human is the storage device. Basically, these people, right? These workers, these office workers, they were part of the storage. They were sort of like reading, writing heads. Basically, they were part of the machine. You see, they had a. So if somebody came to reference this is like Statistics Bureau. They need a reference, and they were brought to the right filing cabinet. They bring it out, right, and then brings the data to the right. So it worked. It was considered cutting edge for the time, right? Pretty nice. So yeah, these days we have, we store our data on clouds, right? And what the heck is a cloud? Well, it's just basically somebody else's computer, really. That's all it is, really, right? And you say, oh, cloud, but no, it's just somebody's computer. You know, Amazon, Google, or Microsoft, or your friend's computer. You can say that's cloud too. It's a small cloud, right? So, yeah. Now, so we go to data storage history to programming language history, right? So I was saying we were connecting zeros and ones in 40s. We move on to primitive languages. Some of them are still around, like Fortran, even Lisp, well, COBOL even somewhere, right? But assemblers, very simple instructions. And when we get to this algo languages, we get to B, C, Pascal, Basic. Maybe some of you have seen actually Basic still around somewhere. Right, but we actually get to 1990s. We get Python. So Python is a relatively latecomer, but it's actually, if we get to next slide, yeah, no, we don't get yet, but we'll see. It's one of the actually most popular language by now, right? It's #1 language, and it's due mostly for what? It's basically because it is quite readable. It's the closest thing to a programming language to human, sort of say how we would write the instructions on a piece of paper, basically, right? It's still it's a full language, but also serves it's extremely readable. Right, so we have many other languages, very interesting, of course, but not for this course. Right, yeah, so Python was created by Guido van Rossum, right? He worked in Netherlands at university, but later on Google, he worked at Google, then Dropbox made him an offer he could not refuse. Who has Dropbox? Dropbox is written in Python, basically all the front end was written in Python. And then he retired a couple years ago, and now he's back at Microsoft. So again, he might get, I guess, another offer, because Microsoft is really big on Python, which is a good thing. I much prefer to Basic, right? So many of their tools, even Excel, even I think even Excel is getting Python. All the business tools, many different tools are getting Python support actually, right? So much more preferable to some specific language for that tool, right? So even some other programs too. I forget now. Is Blender in Python? Even some other tools also help using Python for automation. So Python, again, you can see it here. This is actually ends in 2018, but it's still going up, right? Python is #1 language. JavaScript is right up there as well, of course, right? So again, because it's everywhere, right? If JavaScript is popular because it's in a browser, you have no choice, right? Python is by choice, because Python, as you will see, it has a different syntax than other language. All the other popular languages have so-called C syntax. As you remember your JavaScript, right? Those who had JavaScript course part, it has the curly braces, right? Kind of specific style. And that is not. Python is against overuse of curly braces, right? It tries to save them, right? It leads to more, I would say, cleaner looking code, which is a big thing actually. Language might do the same thing, but one language is all extras, kind of crazy symbols, right? It's not as nice to use, right? Again, there's some languages that are very cryptic. You can be very productive as yourself, but they can be called write-only language. You write it when it's late at night and you are, you drank 3 cups of coffee, right? But then the next morning you don't know why that thing works, right? Python, there's a good chance you'll find your own code. You'll figure out what it was doing, and more importantly, what your friend or colleague or coworker did, because these days, of course, we all work together, right? Collaboration, so very important. So that's why Python has won. Of course, big part, of course, machine learning. Python is the language, the lingua franca of machine learning, deep learning, but other applications as well. So, do I have any slide? No, I don't have slide here. We'll go to the next slides in a moment. But it's basically language number 2 for everything, meaning there might be some language which is more specialized, like there's R for statistics. Right? It's very good language, but it's very good for statistics. It's not so good for, say, web development. If you need a web server, you're not going to use R. But Python, you can do very good statistics with web server, right? And with machine learning, and maybe with web scraping. Maybe you can write also some nice, convert them to PowerPoint slides. You can do all kinds of things with Python together. So its power comes from these different libraries working together. That's one of the things, like the whole ecosystem. As we say, batteries included. So yeah, so this is a short history lesson, right? At least the Python. I think I have one more, how computers in Python work. Yeah, this is actually, I think my slide titles are in Latvian, but of course, since I am speaking in English, right? So you will see this. Okay, yeah. So the syntax, we'll see maybe a little bit of syntax here. This is the old syntax here in these slides. This is how computers, where are we here? This one here. How computers and Python programming works, right? This one here. Yeah, so, again, yeah. On this is a cool XKCD, is a nice comic, science comic. I think he's an astronomer, used to be, but now he writes comics for different science topics, right? And of course, he's a big fan of Python. So print hello world, like getting started, is really simple. Well, like now we do have now parentheses. Old Python, old version used to have no parentheses. Now we need parentheses, but that's only like one of the big changes, right? So. So we're going to learn the basics of programming, right? What's programming? It's basically, well, the act of creating a computer program of instructions for a computer. But what I like to say, automate, yeah, correct, yeah. So it's a way of saying how to make computer do what we want, right? Also, during this course, we will learn how to divide the problem in smaller segments, because that's part of the programming. You want to divide the problem into some smaller sub-problems, and of course eventually you get to some piece which you can solve and have clear instructions. Also, Python is great. Why Python is so popular? Of course, you can automate the boring stuff. One of the examples I give, somebody has a task to cut faces and create headshots from some pictures. I mean, you can do it in Photoshop by hand. Now, of course, you can even write the script in Photoshop, but in Python it's like 5 lines, basically. A loop, simple loop, cut, some simple library import, and easy job. And if it's a job, he can go home and sleep, right? So, yeah, because again, they're saying software is eating up the world, right? This was actually written, I think you might see in this slide as well. Mark Anderson. Who was Mark Anderson? Who remembers? Or maybe his first time? Who was he? He's a venture capitalist now, right? Like a billionaire. But he actually, in 90s, what did he do? What do you think? He was not a Python programmer, by the way. He wrote something called Netscape Navigator, right? So one of the first world browsers, right? Web browsers, right? And later on, from that browser, he already had left by that time. What browser came from Netscape Navigator? Which one do you think?
Firefox?
Yes, Firefox. Yeah, Firefox came from Navigator, from the ashes of Navigator. It was born. So, but his point was this, that pretty much any field, no matter, you can't really avoid the field of software, basically, right? No matter what, you're a researcher, student, of course, obviously, but even if you are a beekeeper or or I don't know, agricultural worker or a dentist, you'll still encounter software, and it's most likely, if you are familiar with working with software, it will make your life better. But if you are sort of like afraid or not really, well, you might be left behind a little bit. So, right, and of course, similarly, we have data. Again, we have huge amounts of data. Again, in research and humanities, of course, we need to process data. Usually, it just sits somewhere. There are, of course, ethical concerns, how to use it best, how to use it. Yeah, but yeah. So we get to the computer, and this is analogy. It says a computer is like a child that is very obedient but very specific, particular. So I don't know if my children are not like that actually. I don't know if this analogy holds, because they're not so particular. They will do, you say one thing, they will do another thing. I don't know, right? I would not mind actually. I don't know if I would want to. Maybe at least one of my children would be like this. I don't know. You just give them instructions, they do it, right? But yeah, you have to be very particular. And again, if you forget some instructions, right, then computer will not do what you want. Now, this is just a short refresher on hardware. We all know what hardware is. So where does all the work happen in a computer? Where does actually instructions are processed? In a Well, RAM holds the data, it holds the data, but this work doesn't happen in RAM. In a CPU, or it says here microprocessor, it's basically CPU, what we call the CPU, right? Of course, these days, work will happen also in a graphical card as well. You can say GPU, right? Some sort of machine learning stuff, right? But CPU, right? Intel AMD, or ARM, or M1 for Mac users, right? M3, right? That's what does the actual work. Right, and also I mentioned this slide. One thing which may be slightly misleading is there's only one microprocessor. Well, maybe you buy one CPU, right? There's one CPU, but what's inside? Increasingly, what do we have? We have multiple cores, right? We think of 4 cores, 8 cores, right? This is pretty old computer, right? I have only 6 cores in this one, right? And 12 threads, right? 6 cores, 12 threads. So this means actually the CPU, right, has 6 inside the CPU. There's 6 actual processing units, right? And each processing unit has ability to sort of switch between 2 tasks, sort of, right? But yeah, but these days it's not uncommon to have 8, 16 core processors. You can even buy a laptop with a laptop you can probably buy with 16, maybe 20 cores, right? But at home, for servers, you can buy for 32, 64, even 96 actually now. It's so why is this growth in cores important? What's significant? Because physics. We don't have any way of increasing the speed gigahertz, right? What's gigahertz? Giga. What does it mean? Giga, number-wise.
That's bigger than another.
Yeah, I like that. I love that. Yeah. So we have what? Kilo? That's 1,000.
Yeah.
Mega
giga.
is, yeah, exactly. So kilo, mega, giga. So mega is millions, giga is billions, milliard Latvian, yeah? Right. So this means about 3,000, well, 2.6 billion operations a second on one core. That's not much these days, right? But you can buy with a computer which goes to like 6 gigahertz at home, but still the problem is physics. If you start going beyond 5-6 gigahertz, the power requirements become really huge. We actually encounter problems, and we can't really, for last 15 years, there are 4 or 5 gigahertz computers like almost 20 years ago. So we haven't really made much progress on that front. We can sort of make things maybe a little more efficient, right? And also, if you can go faster, we just make more cars, right? It's like we have one car, right? You make more cars, right? So that's something significant. Sometimes it leads to, as far as programming, well, Python famously can only do one core, like a normal processing. There's ways of changing that actually, but in overall it's just one core, right? It can only utilize one core at a time. Actually, there's specific reasons for that, but yeah. So this increasingly becomes more important as more cores. You have 16 cores and only one core is doing the work. You know, well, but solution. You need to process files. One thing easy ways to do is to run the same program 16 times, and those type of problems are called trivially parallelizable, meaning trivially parallel, meaning they're easy to work in parallel because they don't depend on each other. And the big problem is for some tasks, some problems, you can't do that, right? One part of the problem depends on another part of the problem, right? And you can't run 16 things at once. You have to run them one at a time, actually. And that's why this current trend towards more cores it does not give you this big improvement as you would wish, right? It's not, right? Yeah, it's so. Now, that's the main part. So we mentioned RAM. So RAM is for storage. We can call this, I would say, like a short-term storage. I would say like a today's storage, I would say. Why? Because what's the story with RAM? It's pretty fast, right? You know, we have pretty large amounts of it. But what's the problem with RAM? Yes, exactly. You turn off the power unless you have UPS, but then still it goes off. You lose data. So what do you need? You need some longer term storage. So what do you use? SSD or spinning Rust or a hard drive. So how many people still have spinning Rust drives or spinning hard drives? Anyone? No one. You still have it here?
No, not here, but at home. I just connected to computer with USB.
Okay, yes, so yeah, that's what's going to lead you. Because I ask, why would you want to use a hard drive, right? Well, there's a couple of reasons. One, well, it's a little bit cheaper, right? Yeah, right, still cheaper. And especially for things like movies or for music, actually, the speed difference is not that, actually, the SSD doesn't give you these big improvements, right? You're still watching the movie at constant speed. And hard drives are great for giving you like one big data file in a succession. SSDs have this big, why are they so nice? They are kind of similar to RAM, that they can go to specific location very quickly. A hard drive has a physical arm or multiple arms. It has to move, right? So you can't get the data. It's physically, it's like milliseconds, like 1,000 seconds, which is slow. Computers, 1 millisecond, that is slow. You want, microseconds or nanoseconds, right? So, but there's still room. And there's another thing is, I don't know how many of you had a SSD fail on you. Anyone? You've had failure? Anyone else? No? But yeah, the problem with SSDs, usually there's not much warning. If it fails, and that's it. You are basically done for, right? So unless you had backups, right, somewhere, right, for your thesis, right? Sorry, right? So it's hard to record data. It does not give you warning, and also it turns out this technology behind SSDs is same as for flash drives, right? If you have your flash drive of your wedding in a closet somewhere, you should plug it in every few years, because the data from this technology, from this flash technology, you lose data quicker. Meaning every few years, basically you need to refresh it. Like hard drive for archives, it's a good choice. It could stand 20, 30 years. It will still preserve data. Of course, if you need longer storage, you might need maybe tapes, which is very slow technology, but it can be used for archives. Well, what else could be used for archiving data? Well, you could use CDs, but or DVDs, right? They don't store too much. Now you can have Blu-rays, right? They store about 50 gigabytes. And the thing is, don't use regular ones. You need to use special gold-plated, and they're ready for about 50 years. But if you think about it, 50 years, but who is going to have a reader in 50 years, right? To read, that's a problem already. Like floppy drives. So who has used floppy drives? Anyone? Some have used, right? I mean, it used to be such a common technology 20 years ago, but then it disappeared as we have flash drives, right? You don't need floppy drives because, 1,000 or million times less data and slower, right? But some devices, like industrial devices, you still use them for programming. music, some older instruments use them, right? I mean, if it works, why fix it, right? You still need these drives, and we have increasing need to. If you discover some, I don't know, some manuscript, it's saved on a floppy drive, right? You still need to read it, and we are into problems finding these readers, right? Especially the older ones from 70s. So yeah, but yeah, this is just a short introduction to hardware. Let's take a break. Actually, I will talk more. Let's continue at 5:20. Yeah, let's do 5:20. Yeah. Online? I used to during COVID. I used to Teams. It's possible I might start Teams as well. I might do that for maybe next week. I'll do it. Yeah.
Yes, because like we recently have a course.
Yeah.
Now many of us are already working. So
Okay. Yeah. Yeah. I definitely sure. I will do a simulcast on Teams next week.
that
Yeah.
would be great.
Yeah. But I'll be really sad if I only see like one or two persons and everybody will home, right?
We can lecture after this.
Okay, so you will be here.
Sadly.
But what's interesting is I have doing this web course afterwards. I'm also having a lecture after this. On the
Here?
web. No, next building.
But we are staying here.
Oh, you're staying here. Okay, that's really convenient. Yes.
I guess I also do better, but I have to do
Yeah.
two.
Okay, sure. I'll definitely do that then. No problem.
Materiālu tiesa, viņas pat nevar kopš pavasara sakārtot kursus, kur mums ir jāmeklē, es atvainojos. Es visu mūžu atceros, kā man maģistrantūrā pirmajā semestrī, pirmajā sapulcē lasīju runāt, ka man jāslēg savas prioritātes, jo tu tagad studē.
Šogad jau ir, man liekas, jau vairāk sakarīgāk nekā bija pagājušā semestra sākums.
Tas
Nav neviena brīva diena, kas tam ir domāts. Es kaut kā bija rēģināt, ka mēs pagājušo gadu tos dikčātus mēnesis paņemām pagājušo gadu mazāk lekciju. Jā, es tev kaut kā tā viņa teica, ka tāpēc, ka mums ir tik daudz lekciju, tāpēc, ka kas ir jāpaņem pirmajā semestrī, nebūs otrajā semestrī viņam iespēja. Kas tad ir?
Viņiem, man liekas, skatījos, viņi kā otrā grupa, lai viņiem mazāk kursu mākušies, viņiem nav mākušies. Tā ir tas pirmais kurs, tas, kas tagad sāk. Viņi tikai otrā grupa. Jo viņiem tur bija tie kursi, kas bija pagājušo semestrī, bet viņiem bija mazāk, man liekas.
Viņiem varētu nebūt tikai mūsu digitālās komentāras.
Jā, mās viņiem nebija.
Viņi teica,
Tās ir nav sapratus, ko es studēju.
Kā, varbūt tu maģistru, ko rakstīs.
Bet ir tas, kas es teikšu pastāstīt, es tik pasauli literatūru, man ir tik
Es teicu, Anē, prasīju, vai ir kaut kāds variants, ka es viņu dotu, piemēram, tēmas, par ko es gribētu, un man var kāds pateikt, vai tas dar vai nedar. Viņš man pasūtīja lasīt handbuku. Tur nekas nav par to rakstīt.
Man vīrs teica, atrod, kurš tev patīk pasniedzējs. Viņš šoreiz raksta savu doktoru, viņa vajadzēs svešnieku, kas neko
Bet tu jau nevari šitā, tāpēc, ka kur tu izvēlēsies savus kurēnu un
Viņš tev pateiks, kur viņš strādā.
Tēmē jau tev vēl patās, jo viņš strādā te. Pasniedzies, kas tu Wikipēdijā. Viņš kaut cik nedara.
Viņš ir kaut ko.
Nu jā, bet tu kādu.
Nu jā, man arī.
Mums jau vajag, tev jābūt tēma tāpatās. Tu vari paņemt tēmu, tajā tur savā virzienā, un tad es domāju, ka tu gribi tikai tutoriem kaut kādu aplikāciju izdarīt, un tad man pasniedzies, kurš var tev palīdzēt.
Stalko. Stalko. Man vispār atrasā jau neko izsaka.
Man mums ir bērni drīz, kurš tagad man visināt laika papīru, es gribu patīties, kā mums te darbi, ko citi rakstījuši. Nu, kas ir? Nu, vai ne?
Alright, so we'll start and continue in a minute.
Vienkārši izvēlēs pasniedzēju un apjautāju uz viņu, kā viņam šķiet.
Let's see. Alright, so I guess we'll continue. I'd like to finish by 6 actually, so we can get the next lecture. So I was just looking at the Blender API. Right, so Blender, I was right, Blender is using Python, so you can almost do everything with Python. You don't have to use Blender, you can use Python to program Blender basically. Alright, so it's just one of the many ways of using Python basically. Right, I just heard people talking about Blender. So yeah, it's kind of a be interesting usage. But let's go back to our hardware. This short primer, of course. So input, well, of course, how do we input data? You know, keyboard, mouse, right? Obviously, scanner, maybe less. We can have also, of course, what's missing in this picture actually? What's missing in this picture? What I think is what would be needed.
User.
User, yes, there's some human there, right? But what else? What this is like maybe 30 years ago. This could be okay. Yeah, this is a powerful computer, but these days it's almost impossible to imagine a computer without something else. What part is missing here?
Graphical card?
Yeah, there's graphical card. Okay, let's imagine it's built into CPU. But no, put something else. What else? What part is missing? Microphone is good. No, it would be good to have. But let's imagine it's a monitor. Also good, but something else which is...
Essential?
Excuse me?
More essential something?
Yes, more essential. You can't live without it.
Phone.
Yes, you could say phone, but it's yeah, what's that meaning? Not phone, not exactly phone, but
USB?
USB is there, but okay.
There is no internet?
Yeah, there's no connection on internet. There's no network connection, right? So it could be an internet, local network, but at least, you know, it's hard to imagine a computer which sits alone, maybe like an atomic station, maybe, right? Nuclear station, maybe. But basically all computers have some sort of networking built in, right? You know, internet, right? Web. So that's something which is, you know, part. There's a, you know, there should be a network connection, right? So that's how we get data in as well, obviously. Right, and output, of course, these days, of course, monitor is your main. Speakers, printer, plotter, maybe some other ways, right? But of course, you might be just you know, sending that somewhere also on a network somewhere. Okay, but that's basically it of the hardware, just a refresher. And now we get to the language. How do we speak to our computers? We need a language, right? And we don't want to write this 001000, right? For those who are observant, notice there's 8 of them, right? So 8 bits make 1 byte, right? 1 byte. 8 bits, 1 byte. So again, this is just for organizational purpose originally, right? To have nice 8 pieces of information. It turns out you can storing your most basic storage block is 0 or 1. Just, yes, no, red, black, just 1 bit. Question will be, is there any other ways of storing data? It turns out in late 1950s, Soviet Union had an experimental computer which had 3 states, 0, 1, 2. So yes, no, maybe, right? And the question is actually, how did it work? Actually, it turns out it's pretty interesting. It worked pretty well, but of course there's no real demand for it. It was experimental and it sort of died away. But it turns out, you could emulate it, right? You could say, okay, you can store 0, 1, right? You have 2 bits and store this extra information, this extra bit separately, right? But as far as economics, as practicality, 0, 1, right, is our basic building block, because you can build anything from that, right? You put them 8 of them together. What do you get? You get byte. So how many different values can 1 byte get? How many? You have 8 bits in a byte.
Then it's 8.
How many?
8? No.
Well, there's 8 bits, 8 zeros and ones. 256. So if you have why is that number? Where do I get that number? 8 bits, it's 8 bit. 2 to the 8, exactly, very good. 2 to the 8, 2 times 2 times 2 times 2 times 2, because there's 2 ways of selecting 1 bit, two ways of selecting another bit, 2 ways of selecting another bit, so 8 times, 2 8 times, 2 to the 8th power, right? Not 2 8 times, but 2 multiplied by itself 8 times, which is 2 to the 8, which is 256. Very significant number. Leads to actually, originally you told us this was a great sufficient way of storing letters, right? 256 letters. We have English language has only 26, right? But we have a space for lowercase. But then, of course, we have other languages, right? And turns out it's not enough, right? You need more than 256, right? You need couple bytes, 4 bytes actually, right? You add emojis, right? So you need more. But luckily, again, luckily, of course, Python offers this built-in. But to the right side, the point is that we want the humanly readable code, right? This is a nice little loop, short loop for Python, and we get nice hello world 5 times, right? From what do you think it will print? Hello world. And what do you think? Those who have experimented with Python, what will be printed first? What number? What's I? 0 first, indeed, yes. Well, but we'll see this in action. We'll see this action. Don't worry if you have not done anything in Python. That's fine. Yeah, my favorite analogy with abstractions. What we do is we code is building abstractions. If I am switching light here, right? I don't really want to worry about physics. I don't want to worry about physics. I might be interested in physics, but I don't have to know about physics to know that it's it's going to work. Hopefully, right? In fact, it could be that there's no direct connection. It could be this is just a switch to a computer, and I'm sending a signal to some smart home, some device, and it's going to tell it later on to turn on the light, right? This is an abstraction. It hides complexity, right? You don't need to know all these dirty details. Otherwise, we could not function, right? Just imagine you have to think about the building materials or opening the door, how the door opens, right? We couldn't live then, right? In a modern world. So yeah, taking this discussion on abstractions, I don't know if you've seen this picture, but left side, what kind of car is that on left side? Do you know the make? On right side, I said right side.
On the left side?
Yes.
What before?
Yes, I don't know what, but you got it right. It's a Ford.
That's the first
But it's
part.
yes, but here the thing, the story goes with Henry Ford said, you can have Ford in any color as long as it's black, right? And this car is red. So I believe this car actually was made for what purpose?
Racing.
No, I believe it's actually a fire engine. I think it is a fire engine. I believe. I'm not 100% sure. You might want to do a reverse lookup and see if it actually is. But the point about these cars, actually, they have some, well, they have some similarities. They have wheels, right? They drive, right? But what's with the left car, right? The Fords, right? It has direct connection. The wheels turn, when you turn the wheel, steering wheel, the actual wheels turn directly, basically. There's very direct connection. There's some mechanics, but yeah. Just like the Soviet Zhiguli, right? It's missing something called power steering, right? There's no power steering. Most of us who drive regular cars, well, we usually have power steering, right? So there's already some abstraction. You turn the car, but it does not turn exactly how you would think, but it turns more because due to the power steering. But now we move on to Tesla, right? On the Tesla wheel is basically a glorified controller, a joystick basically, or a mouse you could think, right? It's a controller. It's sending commands to a computer, Tesla computer, actually multiple computers, right? And it makes decisions to turn. But if the abstraction is done well, you think you are driving just like old Ford or old Zhiguli, right? Old Lada, right? But theoretically, if the computer program goes bad, wrong, you turn right and it will turn left, actually, right? That's when the abstraction breaks down, right? That's the challenge with building good abstractions. You want to hide this complexity. You don't want to leak outside this complexity, right? So, again, for practical purposes, we don't want to get in too deep. And that's why Python is great, because of course we operate on a high level. We don't worry about physics too much. We don't worry about how the hardware was built, right? One slide is going to be enough. We don't worry how the machine code. We don't even have to worry about assembly language, right? We basically are just using a high-level programming language to provide instructions to a computer. We are implementing algorithms. What's an algorithm? How to get out of bed, how to cook an egg, right? That's an algorithm. Different, different tasks, and we end up with an application. Now, so Python is general purpose. What does it mean, general purpose? Well, kind of self-evident, right?
Yeah. Why?
What does it mean? What does it mean to say general purpose? This means, yeah, you can use for anything basically. Yeah, it has a basically extremely wide application. Pretty much, there's almost no limitations. And you might be saying, okay, but is there any other language? Or could it be something very specific? Well, one specific counterexample would be SQL. It's built for database access, basically, right? I mean, you could write Tetris for it, you could write some game for it, but it would be very challenging, right? Same as a language built in Excel, you could do something, but Excel is just for tables, basically. Python is extremely general. Most languages are general, right? But Python is extremely general. Also, I just touched on this. It's high level, meaning the abstractions, the instructions are high level. It doesn't worry too much about what's going on in the hardware level too deep. But next thing is it's interpreted. And what does that mean? What do you think? Interpreted. What could that be? Interpretation.
That's like about readability.
Not only, yeah, but it's actually how the program is run. You basically write your Python program, actually very similar to how JavaScript works, and then when you run it, it goes line by line, and it is interpreted at the moment in time. So you say, what's the other way? Is there any other way? Yes.
Compiled.
Yes, compiled is the other category. It's not. It's actually there is a big sort of say shades of gray, right? But this compiled means you take these instructions and you build machine instructions for everything at once, basically zeros and ones, and you have a basically ready to run program. So is this significant? Well, maybe not too. It's not maybe not too crucial, but it has a how should I say? It's a big factor in speed. Interpreted language is generally slower, right? But you gain this interactivity. You can sort of tinker more. You have this feedback loop, right? You write something, and you can usually just run it again. Much easier. Much easier instead of compiling and then running it separately, right? Actually, there are some languages such as Java, which stands in between. It compiles, but it compiles to like a middle language, like special code language, but bytecode. But yeah, so Python is interpreted. Also, it's dynamically typed. Again, you may say, okay, what does that mean? Basically, it means that data is sort of, we call them duck typing. If it looks like a duck, if it quacks like a duck, yeah, smells like a duck, it is a duck. Basically, our data, the way we store data is basically given appropriate storage, right? It's very flexible, right? We don't tell it how to store data. It's sort of like it works automatically. Well, there are some downsides. Again, it makes the programs a little bit slower for technical reasons, but it's very convenient for writing programs. If you need absolute top performance, Python is not going to be the answer. Okay, now, who is using Python? Well, pretty much everybody. Again, I mentioned this is a language which is basically language number 2 for pretty much anything. Again, different companies using it. It's pretty much everywhere behind the scenes. It's called glue language, so-called, meaning it glues different systems together, right? For example, again, I'll give you the Blender. Blender I probably written in C or C++ or Java maybe, but I don't know which language it is written. But it's used. The Python is used for scripting these different user interactions. It's typically added on to do some extra tasks, sort of like to glue different systems together. Right? That's why it's great for that. Yeah. So it's readable, interactive, interpreted, dynamic, object-oriented. Well, we'll see about that. It's not necessary to write your programs in Python as object-oriented, but it is an object-oriented language. Actually, everything is object in Python. It's portable. What does that mean? What do you think? Well, bless you. So, what's portable?
It's like you can run it on one machine and copy and paste the code in another.
Yeah. And that's all. It should run. It's pretty similar. Again, assuming it's same version, right? It should run. Yeah. Basically, also it has versions on pretty much any computer. Basically, right? Wide variety of hardware. Linux, Mac, Windows, even on a mobile device, even pretty much everywhere. Also, what's interesting is it's extensible in C++. This for this course is not important, maybe, but yes. Part of the power is that many of the things we do in Python is basically using Python to call these low-level languages to do the actual dirty work. Meaning somebody wrote some libraries, such say like NumPy for numerical calculations. It's written mostly in low-level C and C++, but you call this in Python because it's much less painful to use it. Right? You could call it from the other language, but it's much better to use Python. So, so the slow parts of Python actually call the fast running these libraries, and you don't see much slowdown. Actually, you can do some very powerful calculations like for machine learning, right? So it's readable. You kind of get best of the both worlds. Like you can have your cake and eat it too, basically, right? Wouldn't it be nice, right? So yeah, and it is actually nice. Yeah, so one more, this slide is basically a continuation of same story, basically. Yeah, that is mental model. We don't have to think about the low-level details. In fact, this slide from University of Leeds, I wouldn't agree completely with Perl. This is a language which is kind of lower. It's not maybe lower level, but it's less readable than Python by mile. And that's, I think, is one of the reasons why Perl lost. Like in 1990s, Python and Perl was sort of like, you know, competitors. And now it's not contest. Perl is basically not, I wouldn't say forgotten. I think Booking.com still uses Perl. I don't know. If you want a job in Booking.com, you learn Perl, right? But but no, it's not a fun language actually, because it gets kind of really hard to read. And that's one of the reasons why it's downfall. But yeah, so how does it work actually? What's happening underneath? So you have a source code. That's your Python. That's basically a text file, right? You have this Python interpreter, which will interpret this code and run it on your machine, right? Technically, this next slide says actually there is actually a compiler inside. It compiles this virtual machine, but this slide you can safely ignore. This is just a technical detail that's happening underneath. But for our use, we have this slide really, right? You can think of it as a black box. Yes, underneath there is actually interpretation. There is actually a compiler going on, but you don't really see this, right? So yeah, okay, yeah. So this slide we won't need, but I want to show you this last slide. So I mean this one here. What happens in life? What happens in real life? So how can you write a Python program? You can use any text editor. Of course, not Word. Word has its own format, but any notepad or depending how many Mac users. What do you have? Mac users? One Mac user? Nothing wrong with that. No. Yeah, but you have your. I forgot what the name of your text notepad. What you call it? Text editor, some text editor, something like that. Yeah, but yeah, you can use that technically, and I'll show you right now. I'll open Notepad, just regular Notepad, right? This comes with the Windows, right? And I could write print hello world, hello RTU file 2024, right? Text file. I can save it, right? I'll save it. Of course, I'll cheat a little bit. Not I won't cheat, but I will go to my C disk. I have a temp, or let's do temp, right? I have something here, temp, and I'll call this hello September 24, right? Pi, not text. It's still a text file. I saved it, right? You can probably see this, right? Right, and that's a Python program, right? It is a valid Python program, but how do you run it? Well, on my computer, right, I can open up a black screen, right? A command line from 1980s is still present in Windows, right? Control R command. I could go to CD. I can go to CD. What is it? Temp file, temp directory, right? Dir, and I have a whole bunch of these Python files here, and I can do this. I can do Python, right? On hello September 24, and it works. It prints all this. So that's actually, so this would be a way of writing Python programs, right? Are you going to be doing this in this course? No, I don't. I mean, you could, if you want to punish yourself. Yeah, you could. Why don't we do this? Well, because first of all, it's Notepad, right? If I forget this parenthesis, right? What's going to happen? Bad things, right? Nothing bad. I can save it, right? It will run, but it will run with an error. Syntax error. You know, just imagine how painful it will be each time you make an error. This just black text. This is like 1970s, 1980s, before Python was invented, right? You have this, no colors, no hints, no artificial intelligence telling you what to do. Yeah, you get the hint from the interpreter, but that comes too late. I mean, you get a syntax error, and syntax errors these days we catch syntax errors earlier with a good setup, right? So we'll set up a nice development environment, right? So now of course again it will work, right? So yeah, so now explains again. For example, it's not saved. I have to save Control S, right? And it would work, and now it works, right? Yeah. So yeah. This is kind of like, I don't know, how was the analogy doing this? Like, it's like with the eyes closed or something, I don't know, like if you are like good runner, but just running with, I don't know, with cinder blocks tied to yourself or something, I don't know. But yeah, we don't have to do this. But so we need some tooling. Now, since most of you are relatively new to Python, we'll have two ways of working with Python. We could install an IDE, Integrated Development Environment. For starters, I recommend Tony, right? This is a great environment for starting, for learning. Tony, yeah, Python IDE for beginners, right? This is actually from our colleagues in Estonia, Tartu, University of Tartu. I think just one guy, but actually one professor, but he's been working in this project for like 10 years or 15 years. So why do I recommend it? Because this is the easiest way to get full Python development environment on your computer, no matter the machine. Windows, Mac, Linux. So you download Windows for yourself, right? Click download, right? It should start downloading, I believe. No, here. Oh no, not here. But open war. Oh no, Windows, I think, right? Like this. So which one do you want? So you want 64-bit Python 3.10. for Windows, right? That's for Windows users. How about Mac? If I do Mac, you just download this package. Use the one package, yeah, right? Easier even, right? If you are handy with brew install on Mac, you can use brew install Tony. And the beauty of this installation is, that's it. You install one file and you can run it. You install it and you run it, and you'll have something. Once you install it, right? Yeah. Yeah. So you get something like this. Actually, I'll show you. You get something like this the first time you open Tony. I think you'll have something like this. You have a blank screen, right? And you can write your own Python programs. Again, this is a sort of like not very, I would say, not very complicated program. It doesn't have also so much support. It's meant for learning. I'll show you. So how would we write this program? So if you try installing it, this will be your one of your assignments. Like I would recommend, it's not absolutely required, but I would recommend installing Tony. It's because it's so easy. You download and it's there. It's not gonna hurt, right? So if you installed it, right, then you can start writing your programs. Basically, you say new, right? New file. Now print. Hello RTU file 2024, right? Now you see at least some difference, right? You have colors. We got some colors. That's a good thing, right? So if I forget this, right? First of all, it's already sort of like already saying, okay, there's this shadow, right? This also is sort of kind of bad. The colors kind of tell you that it's not so great. That if you're doing some, if this looks good, so let's run it. And it runs here. So this gives you a tighter feedback loop than the previous version, right? You just press run and you get the results back down here, right? Again, it's a very simple IDE. It's actually written in Python. It's kind of funny. This is a Python IDE written in Python. Yeah, you can do things like that. So you can save it, right? Control S. And what I would recommend, you know, I have documents. Make up a folder, my course, my RTU DIP720 or something, right? Folder, and save some files there, right? My Python course, right? And save files, you know, I'll call it September. Hello, September. Right. Right. And we have a program, right? And again, I could still run it from the command line, but for now, for development, I can run it like this. So how many you have, Tony? It takes maybe a couple, I don't know how fast the internet is today. It's about not a very big package. How many you have, Tony, working? Anyone? You have it, okay? Yeah. Of course, if previously, what's the alternative? Actually, we'll see two major alternatives. One, we will be using Colab, Jupyter notebooks, which are interactive notebooks for combining code and text. Actually, I will use them quite a bit in teaching, right? This is just for writing programs to run. And of course, another way is to use more advanced editors such as Visual Studio Code, which you remember. So how many of you still have Visual Studio Code installed? Most of you have, right? So that's another opportunity, and I could show you. If you don't want to, if you already think, okay, this is too easy, right? Because this has some nice features, but it's also very limited, right? You can keep it. It's only like 40-50 megabytes, right? I'll show you if you want to jump into a little bit deeper water, right? I'll show you how you can do it attached to the Visual Studio Code. So since you already have Visual Studio Code, many of you have, right? I'll show you what you need for Visual Studio Code. Maybe we have like 15 minutes, right? So you can skip the Tony part actually. Tau, right? It depends. Like I said, you can do both, right? Or do all three things actually. Okay, so you need, if you remember, you have extensions, right? And you need Python, search for Python. Python language support from Microsoft, 135 million. When I started this course, it had like 20 million. So it's like, you know, 135 million installs, right? This is what you want, and this is the only this is one you need to install, right? But the bad news is why I don't why I usually when I start complete beginners with this why I don't do this immediately. Well, first of all, you have to install Visual Studio Code. That's one step. You need to install this extension. Unfortunately, that's not all. For some reason, well, it does not come with Python. This extension. You have to install Python separately, right? So what do you do? How do you do that? Well, I'll show you. You go to python.org, right? Downloads. Oh, there's a new version, Python 3.12.5 for Windows. Yeah. You see, so it's at least 3 steps, actually like 5 steps. Tony is just 1 step, install, and that's it. This is 3 steps, and I'm going to install it. You can actually have multiple versions of Python on the same computer, actually. Not the end of, it's actually quite common, actually. So I'm going to install this new version, right? Right, so my computer already has Python 3.12, right? It found it here, but so it's going to update for me. I have like 3.12, 4 or 3. For you, if you don't have it, it's going to start a new place. This is a place where it's installed for all users. There's another location. If you just install it locally to yourself, meaning it's not your computer, you want to install to somebody else, meaning it's for just for one user, it will provide something like C users, your name, app data, some like this type of long direction. I like this approach for everybody, right? Install for everybody on your own. Do you want to allow this app to make change to your device? It's Python Software Foundation. Those are the good guys, right? Verified publisher. Okay, let's go for it. Yeah. Initially, it's not again. Python is not a big program itself. While it's installing, I'll show you how big it is actually. Takes like maybe 1 minute. Maybe 2 minutes, maybe 3 minutes. No, looks like it's okay. If we all have SSDs, right? It'll go fast. What is that computer you're using? Oh, it's Raspberry Pi, yeah, right. By the way, Raspberry Pi has, it comes with the Tony, it has like an interface. I mean, it comes with, when you buy Raspberry Pi, there's a special version of Tony for Raspberry Pi, actually. Right, it's kind of cool. This looks cool. Yeah, it looks cool.
Very portable.
Yeah.
And the battery lasts for 8 hours.
Uh-huh. Cool. Very cool. We'll see. Again, I don't have a very fast computer, but it looks like it's going to be finished in a moment, right? So yeah, so this is a little bit slower. And then I'll show you one last step before then we'll be done for today. What's important, once you install Python, we'll have to connect the tell Visual Studio Code where to find Python. And that's slightly tricky, but it's not too tricky, I'll show you. And in this case, looks like there's some new additions. So what's happening right now, if you read this, the message pre-compiling standard library. So what's doing, it's compiling, right? Because Python is written in C language, actually. It's compiling the library parts, actually. So they don't have to run them from Python, actually. It runs from the low-level language. But as a end user, you don't see that. I hope everything works correctly. Okay, setup was successful, right? Usually it's about, I'd say 99% of students, everything is, so we have installed, but the question, where is it? So I'll show you, right? You go to your computer, so it was in C drive, right? You see it's all red, I'm out of space, I need a new SSD, right, on this computer, right? So, it's installed in where? Program files, Python, right? And I have Python 3.9, 3.11, 3.12. I have like 4 years of Python. So it's here. It should be this one here. 8.6. This is August version, meaning yeah, August. Installed today, right? 550. Yeah. So this, the program, the Python, this is the interpreter, Python.exe, right? On Windows, on Mac, it's just Python. On Linux also. It's only 102 kilobytes long, so really tiny. The interpreter, the program which interprets your code you write, it's really tiny. It's only 100 kilobytes long, actually. Well, there is something else. There is also a Python 3.12 DLL. That's a library. That's about 6 megabytes. That's longer. That's extra stuff. There's also libs here, right? So there's probably some extra libs, right? Maybe some includes, some DLLs, right? 14 megabytes. But overall, if you check, let's check properties. Well, 280 megabytes, right? All the extra stuff. But the actual interpreter is only 100 kilobytes. That's really small for a program, right? So again, there's another location where it could be installed. I'll show you users, my name, well, right? Up data. Right, that's, I don't like installing here. I believe it's local programs, I believe, Python. Yeah, so this is like 6 folders deep. So this is a local installation just for this user. I don't really like doing this. Sometimes if you have like a really locked down laptop from like a work or something, you can't install for everybody. You don't have admin access. You can. That's the only option you have. But I don't like it because it's a long way to find your Python. So now we know where Python lives, right? It should live. The most recent one lives here. Python here, right? We will know this location to run our program. So I'm going to install. So I have my Python installed here. I'm going to make a. I'll open up a folder, right? Well, actually, I should open a GitHub folder, but I'll just open any folder. Right, I'll open a folder. Let's open folder. I'll make a new one actually. I'll open and go documents, right? Documents. I'll open my Python course. Okay, sure, why not, right? My Python course, right? Right. And it's full of Py files actually already. That's nice, right? Full of Py files. But most of you are familiar with Visual Studio Code. You see the files, right? You need to tell. You have this little run. You see, you have all kinds of things here. It's the integrated development environment. You don't have any problems, right? You want to press this, run this code, right? It works for me, right? But notice here what happened when I press this. If you look at this here, right? It ran old version of Python 3.11, last year's version, right? Because my instructions are not current on this computer, this 3.12, I have not told it. So how do I do this? What you need is Control-Shift-P, I believe. Yes, Control-Shift-P on a Windows. I think Command-Shift on Mac, right? P. So it's like a search. It's like a search just for Visual Studio Code, and you want select interpreter here, right? And what you need is, you see, selected interpreted. If you have a completely new installation, you have nothing, right? I have already the old one, but you need enter interpreter path, right? In fact, actually, it actually recommends this, right? It found it, but it's possible it does not find it immediately. Enter interpreter path, find or browse. Let's do browse, and I'll tell it. Like I said, I'm doing this because, for you guys, because it already told me it knows where to find my Python. So I'll go here, and you say, okay, this is my Python. This is what you run this Python, right? You tell it, and select interpreter here, this box here, right? And now, if I run it, let's try this again. You see, Python 3.12. So it's telling exactly, okay, when you press this play button, run Python the 3.12, which lives in program files, Python 3.12 folder. Again, this could be any, you could put any folder you want, right? You can install somewhere else, but this is the default location. Okay, and then you are good to go. You can use Visual Studio Code. Again, you have nice Copilot support, right? You can write your let AI write your homework for you, right? So, but hopefully not all of it. I'll still want your comments, right? So this is the best way to work. I mean, again, I'm biased because I've been using this for a while. Yes, there are other options, by the way. You could use there's something called no, I forget now. I'll have a look at desktop. PyCharm. This is actually, if you're a student, there's a free professional version. It costs like 300 euros a year, but it's free for students. It's a really nice idea, but Visual Studio Code is the standard. There's one more other way of running. It's cloud-based, but we'll cover that next time when we work actually on Python. So if you can manage install, if you have Visual Studio Code, install Python, try hooking up Control-Shift-P and find interpreter path. Again, if you can't remember exact what I did, I'm gonna save this video and you can go back and see what I did basically, right? So for next week, let's try to install again Tony. You can work on Tony. That's the easiest. I don't have to think of it all. Visual Studio Code, I think, is much more powerful. Has much better error handling, basically, because it picks up on errors, right? What else? On next week, we will look at the basics of Python language itself, variables, how to store them, we have print hello, and also we'll look at the cloud version. All right, that will be all for today, actually. Thank you all. And also, like I said, somebody mentioned there, I will try to do a simulcast on Zoom, on Teams, not on Zoom, on Teams. It will be on Teams. I'll send a link. But I still, hopefully, most of you will be here, I hope. Right, thank you.
Thank you.
Yeah.
Thank you.
Yeah.